Those are online. Just keep revising the previous topics that we discussed. பாஸ்கர் இந்த ஒரே ரொட்டி கூப்பிட்டேன். பாஸ்கர் இங்க இருக்காரு. அவர்கிட்ட பாஸ்கர் எனக்கு கேல்வன் மீட்டர் மட்டும் ஒன்று தாயேன். கேல்வன் மீட்டர். பேட்டரி எலிமினேட்டர் கிடைக்குமா நம்மளுக்கு யூஸ் பண்ண முடியுமா? இப்போ இங்கே எங்கே கனெக்ட் பண்ணுறது? வைக்கலாமா? அதுக்கு இது வேணும்ல, நான் பவர் சப்ளை வேணும். ஆ ட்ரை பண்ணலாம். எடுத்து revise the previous class concept.
Doing, sir.
Okay. So right. So those who are online, shall we get started?
Okay, sir.
Sir.
Okay, listen. See, இது வருமா? இது வரணும். Right. Shall we proceed? Yeah. Yes. So the next topic that we are going to discuss is, the name itself is here, right? What is it? It's called as moving coil galvanometer. So it's called as a moving coil galvanometer, which I'm sure everybody would have already seen it, right, in your lab. No? You have seen? Where did you use it? Where do you use the galvanometer? Harini, can you tell me? Sorry? Okay, in which experiments did you use in your lab? You used it in? Not sure. Wheatstone bridge is not a part of your... Sorry? To create? Okay, that is theoretically. You don't, in lab, you don't sit and theoretically, practically create an ammeter on a voltmeter. What do you do? Anyone else? Other? You would have used this, no? Yeah. So where do you use? It's not about direction of current. Can you tell me? What are all the experiments you did in your school? Resistance or resistivity? So you find the resistivity of a wire using a device called as meter bridge. Meter bridge works on which principle? It works on the principle of Wheatstone bridge. Okay. So at that point, you will be using a jockey and all those things, right? Where you will be asked to do some connection to the galvanometer and check out whether there is a current flowing through the galvanometer or not. So if the current through the galvanometer is 0, what do you call that condition as? You call it as balanced Wheatstone bridge. So meter bridge, all the experiments that you're doing are calculated. The results are calculated under the condition of balanced Wheatstone bridge, especially that the ones that you perform using meter bridge. Right? You do that. So there you are going to use this device, no? So what is the device called as? It's called as a moving coil galvanometer. It is written here, see, DC moving coil. So it is going to be a moving coil galvanometer. So how does this work? If you observe here, right? So if you observe at this point, where is the pointer here? It is exactly at the center. Whereas if you take another device like an ammeter or voltmeter, this pointer will not be at the center, rather it will be on the left extreme. Why is it so? So it doesn't do anything, it has nothing to do with the direction of current. It has nothing to do with the direction of current. It only, sorry, 1 minute. It only detects whether current is flowing through the device or not. Okay. So what I've done here is, you have seen what this is, right? You know what this is. This is a battery eliminator, right? So this is going to supply the power. So let me keep it at 2 for now. So I switched it on. What I've done is, to this battery eliminator, to the positive I've connected a wire and the negative I've connected another wire. So what I'm going to do is, I will take those two and place them. See, I'll take a positive wire and place it into this positive terminal. I'll take the negative and place it in the negative. Are you able to see some deflection here? Are you able to see some deflection? It has got deflected completely to the right. Now, what I'm going to do is, if I reverse the polarities, what will happen? The deflection is to the left. So this is one preliminary check that you can do to the galvanometer that is given to you. Sometimes what will happen is, when you're doing the experiment, you will not get the balance point properly. You might think that the connection is wrong. Sometimes what will happen is, the galvanometer that you got might be defective. So to check whether it is working properly or not, first what will you do? You take the positive of the battery eliminator, connected to the positive, and negative and connected to the negative. You will see the deflection in one of the sides. When you reverse the polarity, the deflection should exactly be in the opposite side. If it is not working, the device is not working. Okay. So here what happened is, I have some readings here, right? So for those who are online, see, this is how a galvanometer is going to be. The pointer will be exactly at the center. So I'm going to have some readings here. These readings do not have any units associated with them. They're just numbers. So what I'm trying to say is, if you take an ammeter, right, it will be written as capital A in between. What is the meaning of the capital A? Ampere. Some it will be written as MA, milliampere. Some will be written as mu A, microampere. Similarly, for a voltmeter, V, MV, mu V, it will be written. But here, there is nothing like that. Okay, nothing will be given, because it is not a measuring device. It is only a sensitive device to tell whether current is present or not. It is like a sensor. Are you able to understand that point? Right. Now, having said that, now we'll see what is the theory involved behind this galvanometer. How is the pointer actually able to rotate? Okay. So first, let's understand what a moving coil galvanometer is. Basically, a moving coil galvanometer, it is a device that is used to detect current in the circuit. It is used to detect the current in the circuit. So the commonly used moving coil galvanometer is named so because, why is it called as moving coil galvanometer? Because, as the name suggests, there is going to be a coil inside. And in the previous class, we discussed this concept. When you take a current carrying coil and place it in magnetic field, what is going to happen to it? When you place a current carrying coil in a magnetic field, what is going to happen to it? It will experience torque. If you place a current carrying conductor in magnetic field, it will experience force. What is the difference? When I talk about current carrying conductor is open. Whereas when I talk about a current carrying coil is a closed circuit. It is basically in the form of a loop. So if you take a conductor and wind it completely so that you're able to form a closed shape. If you take the closed shape and place it in the presence of magnetic field, what will happen? It will experience torque. So coils will rotate. Conductors will have a translatory motion. They experience force. Are you able to understand this point? So having said this, if you observe, the commonly used moving coil galvanometer is named so because it uses a current carrying coil that rotates or moves in a magnetic field due to what? So when can an object rotate? Only when there is a torque acting on it. It is rotating because of the torque acting on it. So torque is responsible for rotation. Force is responsible for translation. Okay. Now the next question is, whenever you have any kind of an electrical device in your hand, it should work on some principle. For example, if you take Wheatstone bridge works on which principle? Wheatstone bridge works on the principle of Kirchhoff's laws. Meter bridge works on the principle of Wheatstone bridge, right? So like that, every device will have a principle associated. In a similar way, this device also has a principle which is called as a current carrying coil placed in magnetic field experiences torque. So what is the principle on which it works? A current carrying coil placed in external magnetic field will experience torque. That is the principle. That is why here, if you see the pointer, if you observe the pointer, right, if I take this to be the pointer is not moving like this. The pointer is moving like this. This is rotation. This is translation. So inside the pointer is rotating. Are you able to understand what I'm trying to say? So how is that pointer able to rotate? Because that pointer is connected to the coil, which is experiencing the torque. Okay. So a current carrying coil placed in a magnetic field experiences a current dependent torque. Here, how is the torque? The torque is current dependent. Why we call it as current dependent? Because it is going to be NIBA sin theta, where N is the number of turns in the coil, I is the current passed through the coil, B is the magnetic field, A is the area of the coil, and theta is going to be the orientation between magnetic field and area. Theta is going to be the orientation between magnetic field and area. Are you able to understand this? Right. Now, if you look at the diagrammatic representation of how a moving coil galvanometer looks like, observe. So moving coil galvanometer basically consists of two permanent magnets. Why do you need permanent magnets? To produce magnetic field. So there are two permanent magnets, but they are not in the form of a rectangle or anything. They are cut in the form of a concave shape. So the reason for that curved structure is because you will be able to produce a magnetic field, which is called as a radial magnetic field. So the first question to be asked is, you have two permanent magnets. How are those two permanent magnets? They are not like this. Rather, they are bent like this. So what happens with this? There is going to be magnetic field, which is always directed towards one point, which we call it as the radial magnetic field. Are you able to understand that point? Now the next question is, in the presence of magnetic field, what are we supposed to place? We need to place a current carrying coil. So where is the current carrying coil placed? This is actually the top view. And this is the side view. So this is the side view and this is going to be the top view. So when you see it from here, how does it look like? Basically, when you look at it, this is the side view. When you see from here, it is going to be the top view. Right? So we are actually seeing it from here, this side. Are you able to understand? So you have a soft iron core. You have a what core? Soft iron core. See, iron comes into picture. Basically, iron is a substance called as ferromagnetic substance. If you know what is a ferromagnetic substance, those substances are the ones which can acquire and retain magnetism for a longer duration. They can acquire magnetism faster. They can retain magnetism for a longer duration. So those are ferromagnetic substance. In that itself, you have two types. One is called soft iron core and the second is called hard iron core. So when you talk about the soft iron core is used here because due to this magnetic field which is generated by the already existing magnets, this iron core is there. No, that will also get magnetized. What will happen? That will also get magnetized. Are you able to understand what I mean by it will get magnetized? See, suppose this key is there, no? This key is there. If I take a magnet and connect to it, right? Through this, if I try to connect to another object which is ferromagnetic in nature, it will start attracting those objects. Then, if I remove that magnet, right, you can see that the attraction will exist at least for a few seconds. Why is it happening? Because this is able to retain the magnetism. Okay, now listen to all these points. These are all very important points because this is what will come in the assertion reason. So what did I say? Why do we use a soft iron core? Because we don't want the magnetism to be retained in it for a longer duration. What is the objective of a galvanometer? Is it to create more magnetism in soft iron core or is it to detect the current? Detect the current. So we have nothing to do with the soft iron, with the iron core. So we need to ensure we choose a material which is not retaining magnetism for a longer duration. That is why it is used. So around that soft iron core, the wire is wound. Around the soft iron core, the wire is wound. You're able to see this wire, this pink color lines, 3 lines are there. So that is a wire. And there is a circular kind of spring that is used, which is called as hairspring. So to that wire and the hairspring, the pointer is connected. So the pointer is connected through this. So that my question is one thing. See, when you saw this, right, when you saw the activity, when I connect the positive terminal here and negative here, the pointer went to the extreme, right? It went till here. But whereas when I cut the connection immediately, what happened? The pointer came back to its original position. Can I say that there is some restoring something that is existing? I don't know what is that restoring force, restoring energy or something, I don't know. But there is something that is helping the pointer to get restored to its original position. So who is doing it? The spring. Are you able to understand? So basically, the construction is very simple. What does it have? Let's come from the beginning. Let's just summarize it. What does it have? It has 2 permanent magnets. And how are those 2 permanent magnets? They are cut in the form of a concave shape. And why is that concave shape produced? To produce a radial magnetic field. Okay. Secondly, in between these 2 magnets, there is a soft iron core that is placed. And why do we use a soft iron core? Because we don't want the magnetism to be retained for a longer duration. Around the soft iron core, what is wound? There is a wire that is wound. And on to that wire, what is connected? Pointer with the help of a circular spring. What is it called as? Hair spring. H-A-I-R, hair spring. So what does the hair spring do? It creates the restoring. I told you that something, no, it creates the restoring torque. That is the one which will actually pull back the pointer to 0 as soon as the current is cut off. Are you able to understand this? So this is the simple structural diagram. Am I clear with this? Now, if you look at the same thing from a side view, it is the same logic again. You have the pointer, right? You have the permanent magnet between which you're able to visualize this thing now. You're able to observe this is how the soft iron core will look. It will look in the form of a cylinder. Around this, there is a wire that is wound. We call it as a coil, right? And you have a hairspring which is connected to this pointer, which is going to bring back the pointer to 0 as soon as the current is cut off. Clear with this? You can make a note till this point. Okay. Can write it. Did you write down all the points? Draw the diagram. Draw the diagram. This is the one which is given in your textbook. The left side one is the one which is given in your textbook. You can make a note of it. See, actually, the concept is simple, but I have to go in depth for you to understand. Okay. Dehydration. So hot. Still. நீல எப்படி உட்கார்ற தண்ணியை குடிக்காம குடிப்பியா? The throat is fully dry. ஒரு நாள் உனக்கு செமினார் கொடுப்பேன், என்னோட கிளாஸ். சும்மா இது ஜாலியா எடுத்திருக்கேடா, ட்ரை கூட பண்ணாது. டவுட்டா? Shall I proceed?
Okay, sir.
Okay. Yeah, soft iron core is used so that the magnetism is not retained in it. In this, you don't need magnetism. No? You're unnecessarily producing more magnetism. Okay. Because of that magnetism, this will also get magnetized. No. Iron core, what will happen is iron objects have the property of getting magnetized with the help of a magnet. Temporary illa, permanent magnet. If iron core iron in the material, let's say this is some iron material. Okay. This can get magnetized when I place it or when I connect it to a permanent magnet. Okay, you don't need electric current to charge this magnet. So when you take a conductor, let it be a copper or an aluminum conductor, to make it magnetized, you need to pass current. Whereas when you talk about materials like the ferromagnetic substance, which I told, they can actually get magnetized with the help of another permanent magnet also. So through the permanent magnet, there is magnetic field generated. In that magnetic field, if you place the soft iron core, it will get magnetized. It will get magnetized. Okay. And one more thing will happen. See, since the soft iron core is having the, listen to this. Since the soft iron core has the wire will also get magnetized, because current is passing through it. When current is passed through a conductor, it will get magnetized. That will also again magnetize the soft iron core. Due to which what will happen is, if it is too much magnetized, then the torque parameters will not work properly. That is why you choose the material in that order. You're not getting into the manufacturing aspects. Okay, and just to put it clear, soft iron core is used only for that reason. Okay. Now, having said this, if you observe, when current is passed through the conductor, what is going to happen? There will be a torque that will get generated. So what is going to be the torque? Torque will be equal to NIBA sin theta, where theta is going to be what? Theta is going to be the angle between area vector and magnetic field. Okay. Now, if you observe, I told you that the magnetic field that is getting generated is going to be radial in nature. So the meaning of radial magnetic field is the value of theta will always be 90 degrees. Okay, the reason why we are actually generating magnetic field is we want to ensure that the torque experienced by the current carrying coil is always maximum. So who decides the maximum value here? The number of turns inside the coil is fixed. I is dependent on how much current you are passing from the external source. Magnetic field is decided by the concave shaped magnets that you use. Area of the coil is decided by the length of the soft iron core across which you are going to wind. So who is the only parameter that can actually control and make the torque be maximum? That is theta. So what should be the value of theta for torque to be maximum? 90 degrees, because sin 90 is 1. That is the reason why we generate radial magnetic field. This is another important question they will ask you. So what is the reason for you to generate radial magnetic field? So let's come in the sequence again. Concave shape is used to generate radial magnetic field. And why do we have radial magnetic field? To produce maximum torque. So these are the important points you need to have in your mind. So maximum torque by generating the value of theta to be equal to 90 degrees. Did you understand what is the sequence of the story? Am I clear with this? Right? So when theta is equal to 90, if I substitute it here, torque will be equal to NIBA sine of 90, which is going to be NIBA itself. It's going to be NIBA itself, which is going to be equation number 1. Am I clear with this? Am I clear with this point? Now I have a question. If this is going to be the amount of torque that is generated due to the current that is passed through the coil, then what should be the restoring torque that will be able to bring the pointer back to 0? So the restoring torque, can I say it will be directly proportional to the amount of deflection you produce in the coil? Right. So since I use theta here, let me use another symbol. I'll use phi. So what am I trying to say is the restoring torque is directly proportional to the, so it is directly proportional to the angle of deflection. Right, you're able to see, no, with respect to this initial point, how much is going to be the deflection that will take place. So if I remove the proportionality symbol, this is going to be in such a way that the restoring torque is equal to minus k times phi. What does this minus sign indicate? Minus sign indicates that it is opposite. Right? If you see, you would have already learned a concept like this, that F is equal to minus kx in your 11th grade, which is called as restoring force. Similarly, if you replace force with torque, you need to replace linear displacement with angular displacement. That's it. So what I'm trying to say is, in terms of magnitude, see, minus sign indicates that they both are in opposite direction. Okay, accepted. Second point is, I'm trying to say that whatever is a torque that is produced in the pointer due to the passage of current should be exactly equal to the restoring torque that is acting. That is, NIBA should be equal to K times phi. Make sense? Right? Which implies the amount of deflection produced by current is going to have a value. So phi divided by I is equal to NBA divided by K. So this phi divided by I is given a name called as, current sensitivity. This is basically a sensitive device. If current is passed, if it detects that current is there, it is going to show a deflection. So if you want to basically understand what a sensor is, see, you all have gone into lifts, right? In apartments, you go into lift. You press a button. I'm talking about the automatic doors, not the one where you need to manually open it, not the grill gates. There are automatically opening doors, right? When you press the button, the doors automatically get opened. Let's say you're somewhere far. The doors are getting closed, but you have the provision of putting your hand and taking out. Have you done this? If you want to stop the lift, what are you going to do? Either you press the button, or in urgency, you'll try to put your hand and take it out. Due to which, what will happen? The doors will start going back. How is it able to know? It is because of sensors. So as soon as your hand enters, it is detecting that there is some object in between. So it is trying to push the door away. In a similar way, this is also working like a sensor. As soon as it detects, as soon as it understands that current is passing through it. Hand is the example that you can connect here, current. Hand in the lift is the current in the galvanometer. As soon as current is passing through, the pointer will start getting deflected. Okay. So that is the reason why this current sensitivity is a very important parameter for us to understand. So if you actually look at it mathematically, right, what did we write it as? The number of divisions. So phi is the number of divisions divided by I. Meaning, if I pass, listen to this carefully again, listen to this very carefully. If I pass a unit value of current, when I say unit value, I need not always take it as ampere. I can say milliampere, microampere, nanoampere, whatever I want. Unit value of current. So when I pass unit value of current, how much deflection is shown in the galvanometer defines this concept of current sensitivity. Are you able to understand this? Yes or no? Right? So did you all write your record? Did you all finish writing the physics record? Okay, at least did you see what are all the experiments that are there that you need to write? Okay. Did you see something called as, yes or no?
Yes, sir. Yes, sir.
Okay. So there is something called as half deflection method. There is something called as half deflection method with respect to a galvanometer. Do you guys remember seeing that? Did you do any experiment with respect to galvanometer? You don't have lab. Others. Regular school dana. You remember this? You remember something called as figure of merit. You have heard of it? There is a problem with labs. So what we are doing is, you saw this current sensitivity, right? Did you understand the significance of it? What did I say? What is the meaning of current sensitivity? Don't memorize it. What is the meaning of current sensitivity? How much deflection is taking place in a galvanometer when you pass unit value of current? See, just to give you a similarity, right, for you to understand, if I tell you the speed of an object is 2 meters per second, what is the meaning of this? In every 1 second, there is a distance of how much covered? 2 meters. So 2 meters is a distance covered in every second. In a similar way, when you pass unit ampere of current, there is a deflection of this much value shown. You're able to understand this? So that is phi by I, which is called as current sensitivity. Listen to this very carefully. if I exactly write the reciprocal of this, if I write this as I divided by phi, this is going to be K divided by NBA. Basically, it is a reciprocal of current sensitivity, and this parameter is called as figure of merit. But I'm not concerned about the mathematical expression. I need to understand why exactly do we need this. So what the figure of merit is, it exactly tells you the reverse of it. Listen to this very carefully. It will be, understand this, okay? There is a slight difference between them. Try to understand. So what does current sensitivity tell? You pass 1 unit of current, you can calculate how much deflection is experienced. What does figure of merit say? It's a reciprocal. Look at the denominator. Unit deflection, meaning you're able to see the numbers corresponding between each value, right? So if you look at you're able to see the numbers, no? Yeah. So if you look at the numbers here, if 0 is here, and let's say the first division is here, for my pointer to go or travel exactly between a division of 1 unit. What is the meaning? I want my pointer only to travel between a division of 1 unit. When I say 1 unit, it can be between 0 to 1, 1 to 2, 2 to 3. It can be anywhere. So wherever is the initial point of my initial reference point of the pointer, from there, I wanted to travel exactly to the next reading. So to calculate how much, to produce a deflection of 1 unit on the galvanometer, how much current am I supposed to pass defines the concept of figure of merit. So merit has something to do with appreciation, no? When do you say merit? When you clear something in merit, what does that mean? You're good at it, right? So in the similar way, the figure of merit defines how sensitive the galvanometer is. Means for my pointer to go from 0 to 1, even if I pass small amount of current, it is able to create the deflection, then it is said to be a very good device. Because it is sensing very fast. That is the meaning of it. You want me to go only with the book definition? Right? Are you able to understand? Will you remember the significance of both? Can you tell me what it is? So what does current sensitivity define? Current sensitivity basically speaks about how much deflection is suffered when unit value of current is passed. What does figure of merit speak about? To produce unit deflection, how much current are we supposed to pass? They both look similar, but they're not. Okay. So when you look at the unit of it, current sensitivity is measured in terms of division per ampere, whereas figure of merit is defined in terms of ampere per division. At least today, go open your record book or observation book and check what I'm trying to speak. Okay, at least just go through the concept, you'll understand it more. Is the point clear? So these two are very, very, very important parameters that we need to keep in mind. What are they? Current sensitivity and figure of merit. So the third parameter that we need to have in our mind is called as voltage sensitivity. What is it called? It's called voltage sensitivity. So the meaning of voltage sensitivity is deflection per unit volt. See, when current sensitivity is deflection per unit current, voltage sensitivity will be deflection per unit volt. Right? So we know that V is equal to IR. So phi divided by V, you will write it as I into R. So basically what is going to happen is this phi by I is called as current sensitivity. So current sensitivity divided by resistance is what is going to give you voltage sensitivity. So whatever value I have calculated here, that value should be multiplied with R in the denominator. Basically, what is it? It is going to be NBA divided by K into R, and this K is called as torsional constant. Okay, here K is called as spring constant. Here K is called as torsional constant. So have this in your mind. Is that point clear? Right. So now we can. It varies with the windings. However, the spring is wound. எப்படி இருக்குன்னா கேட்கறது இந்த ஸ்ட்ரிங்கோட டென்ஷன் எவ்வளோன்னு கேட்குற மாதிரி இருக்கு. என்னால எப்படி சொல்ல முடியும்? ரைட். இதுவே நான் திக்கா எடுத்தா மாறும்ல. Depends. Guys, are you able to understand? Right.
Yes,
we
sir.
can make a note of it. See, this is a derivation actually. It's not big. There are only two steps. If I have to conclude it, there are only two steps. Right? So if I just have to conclude this derivation, what are the two steps that we need to have in our mind? One is you write the expression for torque in terms of current, number of turns, magnetic field, and area, which is going to be NIBA. And you write another expression for torque in terms of torsional constant, K5. Equate both, you're done. Equate both, just rearrange, you will get three different parameters. What are they? Current sensitivity, figure of merit, and voltage sensitivity. That's it. Okay. So if you're done with this, I'll proceed to the next slide. Solra, is that doubt? Ama. Ama, ஏன்னா ரேடியல் மேக்னெட்டிக் ஃபீல்ட் ஆல்ரெடி உள்ள இருக்குல்ல. Current has nothing to do with torque. நீ என்ன பண்ற ஒரு பாராமீட்டர் ஃபிக்ஸ் பண்ணிருக்க. எந்த பாராமீட்டர் ஃபிக்ஸ் பண்ற? டார்க்கை வந்து மேக்ஸிமம் தீட்டாவை ஃபிக்ஸ் பண்ணிருக்க. நீ தீட்டாவை ஃபிக்ஸ் பண்ண என்ன பிரச்சனை ஆகும் தெரியுமா? It will become a function of two variables. ஒன்னுடா சிம்பிளா யோசிப்பா. நீ நாளைக்கு வந்து லெட்ஸ் சே நீ தான் இந்த இன்ஸ்ட்ருமெண்ட்டை கண்டுபிடிக்கிறேன்னு வச்சுக்கோ. ஓகே, இப்படி இருக்குன்னு வச்சுக்கோ. என்ன லாஜிக் இது? இந்த இன்ஸ்ட்ருமெண்ட்டும் அக்கார்டிங் டு யூ வாட் ஷுட் இட் டூ? கரண்ட் பாஸ் பண்ணா எனக்கு டிஃப்ளெக்ஷன் காட்டணும். ஓகே, ஸோ அப்போ you will try to make this device as a function of how many variables. So இப்போ mathematics student யோசிக்கிறேன்னு வச்சுக்கலாம். இந்த டிவைஸ் வந்து how many parameters should it depend on? நீ என்ன சொன்ன? what is the objective of this? current pass பண்ணா deflection வரும். So what is the important parameter here? current தானே. ஓகே, இப்போ நான் என்ன சொல்றேன்னா, இப்போ டார்க் வந்து ஐயும் இருக்கு தீட்டாவும் இருக்கு. let's say number of turns fixed, magnetic field fixed, ஏன்னா சேம் மேக்னெட் தான் யூஸ் பண்றேன், ஏரியா ஆஃப் காயில் ஃபிக்ஸ்டு. இப்போ இந்த டார்க் வந்து இப்போ தீட்டாவை நான் ஃபிக்ஸ் பண்ணாம வச்சிருந்தா 90க்கு இட் பிகம் டூ வேரியபிள்ஸ். அப்போ என்ன ஆகும்னா the user who is going to use this will get confused unnecessary. அப்போ நீ ப்ராப்ளம் சால்வ் பண்ண இன்னும் ப்ராப்ளம் ஏற்றிட்டு இருக்கேன்னு அர்த்தம். அண்டர்ஸ்டுட்? தட் இஸ் த ரீசன் வை வி ஆர் ட்ரைங் டு ஃபிக்ஸ் த வேல்யூ ஆஃப் தீட்டா டு 90. அதுக்காக தான் அந்த கான்கேவ் ஷேப். Photo எடுத்துக்கோ. இல்ல நான் லாஸ்ட்ல வேணா காட்டுறேன். Just leave some space. Now we have discussed less simple. Okay. So based on this, we can say what are the factors on which the sensitivity of a galvanometer depends on. What does it depend on? It is NBA divided by K. It depends on the number of turns. So when I talk about current sensitivity, phi divided by I, it is going to be equal to NBA divided by K. So if I increase the number of turns, is it going to be a sensitive device or a less sensitive device? Look at it. Phi by I is there, that defines the current sensitivity. So if I increase the number of turns, is it going to be sensitive or less sensitive? More sensitive or less sensitive? How is it proportional? Directly, no. So number of turns, it depends on the magnetic field. It depends on the area of the coil. If any of these three parameters is increased, it can be more sensitive, right? And what should you do to the torsional constant? you should decrease it to become more sensitive because it's inversely proportional. So these are the 4 factors on which the sensitivity of a galvanometer depends on. Am I clear with this? Shall I proceed? Okay. So after this, what we are going to see is, we'll try to understand how to convert a galvanometer to a device called as ammeter. Now, so the next topic of our discussion is going to be about conversion of galvanometer to ammeter, right? Now, if I take a galvanometer like this, remember, galvanometer has a resistance, right? Galvanometer has a resistance, and let me call that resistance as RG. Okay, and I will call the current through the galvanometer as IG, which is called as the full scale deflection current. The meaning of full scale deflection current is, I have a full scale of 30 divisions here. Means if I pass a certain amount of current, my pointer should go till 30. So that's what you call it as full scale deflection current. Okay. This is about the galvanometer. So what is our objective here? I have a galvanometer. I want a galvanometer, which is a sensitive device, to become a measuring device, which is an ammeter. Right. So I need to do some changes with respect to the circuit in this, so that I'm able to make it an ammeter. Listen to this very carefully. Okay. Now, for me to do the conversion, I need to first know what is the requirement. So what is the requirement here? I need to generate an ammeter. So first question that I'll ask is, if you're saying you're going to use an ammeter, how are you going to connect an ammeter in a circuit? How is an ammeter connected across a resistor? It is connected in series. So why do you connect it in series? Because in series, the current is same, because ammeter is a device which is used to measure current. Am I clear with this? Okay. So that I understood. The next question that I need to ask is, should an ammeter have greater resistance or lesser resistance? If I talk about an ideal ammeter, what should be the resistance of it? Listen to this carefully. I have an ideal ammeter. For that ideal ammeter, what is the resistance? It is 0. For an ideal condition, the resistance is going to be 0. Right. So can I say that the resistance of a galvanometer should be very less, because here it is ideal condition, but we cannot achieve this ideal condition. So it is supposed to be less as possible. Makes sense? So which device am I converting it to ammeter? Galvanometer. So galvanometer itself already has a resistance. To that resistance, I need to decrease the value to make it into a device which is having even more lesser resistance. Right. So what I will do is, to this galvanometer, observe this very carefully, I will take another resistor, right? I'll take another resistor and connect it in parallel to this. Why am I doing it? So that this resistance and this resistance, when they are put in parallel, the equivalent resistance will decrease. Because we know that in parallel connection, the equivalent value will decrease, and in series connection, the equivalent value will increase. Okay. So by doing this, what I'm actually trying to say is, if I say that the amount of current, this whole device put together. So when I say the whole device, it is the galvanometer plus this parallel resistor, which is called as shunt resistance. So basically, shunt means diversion of something. So when you say shunt resistor is connected, it is always connected in parallel, because in parallel, what happens? The current gets diverged. So if this whole device, which is called as an ammeter, which is a combination of galvanometer and shunt resistance, right, is going to measure the current I, what is the maximum current that is supposed to pass through this galvanometer? It is Ig, the full scale deflection current. So the remaining current, what will happen to it? It will flow through the shunt resistance. Am I clear? Right. So here, when I say I need to convert a galvanometer to an ammeter, listen to this question very carefully. When I need to do that, I need to do two things. What is it? One is I take the galvanometer and connect the shunt resistance in parallel to the galvanometer. And the second is I need to know what exactly should be the value of the shunt resistance. Because whenever you look at the different, I'm talking about the real-time application, whenever you buy an ammeter from a shop and come, right, you will be able to see the full-scale value on it. For example, if they say 0 to 5 ampere, what is the meaning of it? The least value it can measure is 0, that is when no current is passed. The maximum current it can measure is 5 ampere. So if I say that this current which I want to measure is known to me, then what should be the shunt resistance I need to connect across this galvanometer so that I create an ammeter of that range which I require. So what I'm trying to say is the shunt resistance is what we are going to find in terms of resistance of galvanometer Ig and I. Is the point clear? I'm only telling you the requirements. See, calculation is very, very, very simple. It's very simple. Observe, if I take this point to be A and this to be B, this is C and this is D, how are these two resistors connected? They are in parallel. So when they are in parallel, what will be the potential drop across AB and potential drop across CD? They will be the same. That is the logic I'm going to use. Look at it. VAB is equal to VCD. Makes sense? So what is the resistance of the galvanometer? It is RG. So what is the potential drop across the galvanometer? According to Ohm's law, it is Ig into Rg is equal to, what is the potential drop across the shunt resistance? I minus Ig into RSH. So what should be the value of shunt resistance? Ig into Rg divided by I minus Ig. That's it. So if I need to know what should be the shunt resistance that I need to connect, if you give me a requirement, you say that, sir, the maximum requirement, the maximum current my ammeter is supposed to measure is 10 ampere. What I'll do is I'll take the 10 and substitute it here. For that galvanometer, I'll know Ig, Rg, every value will be known to me. I'll just substitute 10 here so that I'll know what should be the value of shunt resistance that I need to connect across the galvanometer. Did you understand? Just to summarize it, you take a galvanometer, connect a shunt resistance in parallel to the galvanometer. This whole circuit is what is called as ammeter. This whole circuit is what is called as ammeter. And to find the value of shunt resistance, use the concept of the potential drop across two parallel connections will be the same. And it's a two-step derivation. And this result is to be remembered. This result is to be remembered. Have it in your mind. Those who are online, are you able to understand?
Yes, sir.
Yes, sir.
Okay. Clear with this? Okay. So the next one is even more simpler. Okay, we'll just finish it in 3 minutes. Shall I proceed? Yeah. So the next topic that we are going to see is conversion of galvanometer to voltmeter. So the galvanometer's requirement is known. Rg is the resistance of the galvanometer. Ig is going to be the full scale deflection current. These two parameters are fixed. Now my question is, how is a voltmeter connected across any circuit? Voltmeter is connected in parallel, right? And what is the resistance of an ideal voltmeter? For an ideal voltmeter, resistance is infinity. So it will not be infinite. It will be somewhere around 5,000 to 6,000 ohm. It will be a very high value. So what I'm trying to say is, if I have a galvanometer, to this galvanometer, I need to connect an external resistor. But how should I connect that external resistor so that the resistance of this galvanometer is increased? I need to connect it in series. So I take a resistor and connect it in series. Here I wrote it as RS. Don't get confused. In the previous case, I wrote it as RSH. SH stands for shunt. Here RS, S stands for series. Okay. So if you observe, this is going to be the galvanometer's resistance. And what should be the current through this series network? The current through the series network is supposed to be IG. And this whole device put together, the galvanometer plus the shunt resistance put together is called as, this is what is called as voltmeter. Is the point clear? This is what is called as voltmeter. So let us say that this voltmeter, can measure V volts. It can measure V volt. Okay. Can measure V volt. Now listen to this carefully. V should be equal to how much? V is the potential drop between this end and this end, because this whole device put together is a voltmeter. So if I take the potential drop between the ends as V, then V is equal to IR. So what is the value of I that is passing through this device? IG into what is the equivalent resistance here? G plus RS. So what is my job? I need to know how much should be the value of RS. For that, what I will do is I'll take IG to the other side. From here, can I write V divided by IG is equal to G plus S, which implies S is equal to V by IG minus G. 1 minute. I took this as RS, no? Yeah. So G plus RS. So RS should be equal to V divided by IG minus G. So if you know how much is the volt that voltmeter is supposed to measure, suppose it should be 10 volt, substitute 10 here, 10 divided by IG minus G will give you the answer. Okay. So 1 minute, there is a small correction I would like to do here. Actually, I took the resistance of the galvanometer to be Rg, no? So I'll write it as Rg plus Rs, here also Rg plus Rs. So here it will be V by Ig minus Rg. That's it. So as I told you, it is only two-step derivation. Is that clear? Right. So with this, the concept of galvanometer is over. The next part of the chapter that we are supposed to see is called as Ampere's circuital law. So that should take 2 classes. With that, the chapter will be over. Okay. Then I'll solve some problems, some important concepts. After that, we'll move on to the 5th one. From 5th onwards, it is again small only. 5th, 6th, 7th, 8th, we can complete it fast. Okay. Any other questions? Is everything clear? Okay. So revise these topics and come. Tomorrow I'll start with Ampere's circuit. Okay.
Okay, sir.
We'll wind up
Okay,
then.
sir.
Yeah.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah, ma'am. Thank you. Rest room, madam. உள்ள போய் ரைட் பண்ணணும் ஒரு இடம்